All right, so thank you for coming to the seminar, which is online this week. And it's my pleasure to virtually introduce you to Florian Besau from the Technical University in Vienna, who is going to talk about random spherical polytopes. So whenever you want, Florian.
Thank you. Yeah, so let me first of all thank again the organizers of this seminar and the opportunity to speak here about some of my research topics. So I want to present to you some new results on random spherical polytopes. And before I talk about the random polytopes in the spherical geometry, let me just introduce you again to a bit of the more historic classical results in Euclidean space. So let's start with the classical Euclidean setup. So, okay. And just to fix the notation, let's start with the most classical easy setup here. So we want to talk about the Euclidean space in d dimensions. We want to fix some convex body. This is a compact convex set with non-empty interior. And then we want to construct a random polytope model. And the idea is to draw random points from K. And so you want to do this for now uniformly. So we want to draw points with respect to the normalized Lebesgue measure on K. We want to draw them at uniform and independently. So we want for a fixed number of points n to have an array of random points. And then we take the convex hull and this will be our polytope. Okay, so to be more precise and to fix the notation, so x1 to xn will be these independent and uniformly distributed points. They are distributed with respect to the normalized Lebesgue measure, volume measure on K, and then taking the convex hull gives us the random polytope. So these are, this is a very classical setup, and these are very interesting objects to study from different points of view. I want to focus here on the theory when the number of points n goes to infinity. So we will look at it in an asymptotic way. And then you can study the geometric quantities of these random polytopes in a probabilistic sense. And again, I will focus on just a few quantities here that are well known. So for instance, we will look at the volume. So you can take the volume of the random polytopes. This is a random variable. You can take the expectation. And as I was saying, we want to look at it asymptotically. So when the number of points goes to infinity, you would expect this to converge against the volume of your original convex body K. And so the interesting part here is the error term, which tells us now that the rate of convergence is 1 over n to the power 2 over d plus 1. So this controls how fast we are going against the volume of K. And then there is some geometric quantity appearing here, depending on K, the so-called affine surface area. And so the constant here is dependent on some dimensional constant that is known and some geometric quantity on K. Okay, so the error term in this volume approximation, in this expected volume of the random polytope, is controlled by a rate over n with a certain power and some geometric quantities. And this theorem could be attributed to Schütt, or another proof is given by Böritzky, Fodor, and Hook. And it has a long history. So it started basically with Reni and Solanke, I would say, as have many results in this direction. They considered the two-dimensional case for a smooth convex body. This was then subsequently extended into higher dimensions, first by Schneider and Liecker, and then regularity assumptions were dropped up to the point where we could say this holds true for a general convex body K. Now, one has to be a bit careful here. So if you plug in a polytope, if K is a polytope, then it's intrinsically flat almost everywhere. And then this affine surface area, which is a curvature measure, as we will see in a moment, becomes 0. So for some convex bodies, this would be 0 as a constant, and then this would just tell you that the error term here is of an higher rate. It converges faster to 0. Okay, and we will see the polytopal case later on. Just at the moment, let me just say that maybe the most natural way, the most natural setup for this is not the general convex body, but a convex body that is somewhat positively curved in some region. Okay, so what is the affine surface area? And I will not talk too much about this, just to highlight this. So the affine surface area as the name suggests, is an affine invariant geometric quantity of convex body K. One way to define it is as a curvature integral. So you integrate over the boundary with respect to the surface area measure. You can think of it as the d minus one dimensional Hausdorff measure restricted to the boundary. And you integrate some curvature functional. Here we have the Gauss-Kronecker curvature to the power 1 over d plus 1. So the Gauss-Kronecker curvature is basically exists in almost all boundary points for a convex body, and is the product of the principal curvatures. And both of these quantities, the surface area measure and the Gauss-Kronecker curvature, they are Euclidean notions, right? So if you apply a linear, an affine transformation, so a special linear transformation, they are not preserved, they change rather drastically maybe. However, if you combine these two notions in this way, then actually the changes sort of cancel out and you find that this quantity in the end becomes an affine invariant. So this is a very remarkable feature of this quantity. It's not obvious from this definition at all, but from this, well, one way to define affine surface area would be as a limit in this formula up here. And up here, you can immediately see that this has to be an affine invariant, because on the left-hand side here, you have the volume of a convex body. And if you apply a special linear transformation or a translation, so an equi-affine transformation, then the volume does not change. And so the left-hand side here is an affine invariant. So everything on the right-hand side that depends on K also has to be sort of affine invariant. And in this sense, this has to be an affine invariant. Okay, so this is another way to quickly see this affine invariance property of this quantity. But we have a very precise understanding how it is calculated in local sense. Okay, so this is an old quantity. It goes back to Blaschke. It's almost 100 years old now. Blaschke introduced it for smooth convex bodies, and this was then subsequently extended to all convex bodies. There were some competing extensions which turned out to be all equivalent, and basically the question was completely settled on this extension by Monika Ludwig and Matthias Reitzner when they gave a characterization by very basic properties of these quantities. So as I was saying, this functional is equi-affine invariant on the class of convex bodies. It is upper semi-continuous with respect to the Hausdorff Hausdorff distance. And it's additive on convex bodies, finitely additive, which is to say, if you have two convex bodies such that the union is also a convex body, then the affine surface area of the union can be calculated as the affine surface area of each of those parties added up minus the affine surface area of the intersection. So it's not the measure, to be precise, it has some finite additivity property, and usually this is called a valuation then. So we have this characterization of the affine surface area by Ludwig and Reitzner as an upper semi-continuous affine invariant valuation. Okay, and this whole affine surface area was then generalized into a larger family of surface or central affine surface areas. We have seen some LP affine surface areas appearing, and more recently Orlich affine surface areas. We have very important isoperimetric inequalities for these, and further extensions into functional settings, non-Euclidean settings. So this is a very hot topic still. There is a much growing interest in these curvature integrals. Yeah, so this is something I'm also interested, so I wanted to talk a bit about this. But since this is not the main topic today, I will now switch again to our random polytope setup. So affine surface area appears here in the first arrow term as a geometric quantity that controls this constant. Okay, so this gives us information about the volume, the first moment of the volume of the random polytope. And then there is also information on the second moment, on the variance. And this is a result by Reitzner, which tells you there are constants depending on K now, which, so we don't have a limit theorem, but we have sharp constants. And the takeaway is that we have a control in the rate where so we know the variance of the volumes goes to 0 and at this rate, and we have the same rates from above and below. So this is really a sharp bound. Now, this result was also a major step forward because not much was known about the variance of this volume of random polytopes. Only some particular cases were studied before then, and Reitzner gave here sort of a complete picture for the class of convex bodies that are where the boundary is twice differentiable, and each boundary point has a positive Gauss-Kronecker curvature. And using this variance, then it was possible to do also a central limit theorem, where you look at the volume of the random polytope as a random variable, and if you normalize it so that the expectation is 0 and the variance is 1, then in distribution, as the number of points goes to infinity, this will converge to a standard Gaussian random variable. And again, Reitzner pushed the theory forward a lot because central limit theorems were only known in some particular cases. For instance, for in the plane for the unit disk, but he gave this theorem using this variance bounds in the whole generality in all dimensions for any convex body of this class C2+. So this is for the volume of a random polytope what I wanted to highlight here. We have a very clear picture about the first and second moment, and we have a central limit theorem. And moving on, the second case I want to look at is the polytopal case. So we have just looked at convex bodies of class C2+. And if you replace this by polytopes, then the behavior changes. So I mentioned the Efron surface area for a polytope is 0. So you have a faster convergence in the expectation of the volume. And there is a limit theorem due to Radom and Buchter, which gives you a precise information in the same way we have just seen for the general case. The expectation of the volume of these random polytopes inside a fixed polytope converges to the volume of the polytope, and the rate here is almost 1/n. There is some logarithmic term which which makes it a bit slower, and the constant is then controlled essentially by some combinatoric quantity of the polytope P. So this is the flag number of P. So to explain what the flag number is, let me just briefly recall. So if you have a d-dimensional convex polytope, then you can look at the faces of this polytope. So the i-dimensional faces are like in the sketch. So the 0-dimensional faces would be the vertices. The 1-dimensional faces would be edges. And so F0 will be the number of vertices, the number of edges. Fd-1 is then the number of facets. Complete this picture of i-dimensional faces by including the -1-dimensional face, which should be the empty set, and the d-dimensional face, which is the polytope itself. So in this way, you actually generate what's called the face lattice, which is a graded lattice where you have sort of the root, which is the empty set, and you have the top, which is the polytope itself, and then you have for each eye, for each dimension of the face, sort of this can be seen as the ranked function. So you have a ranked lattice, a very nice lattice structure, right? So so an edge in this lattice would be just containment, and then you can look at the maximal chains in this lattice. So you start with the empty set, then you take a vertex, then you take an edge that contains the vertex, then you take a two-face that contains the edge, and so on. So you build a chain in this face lattice, and you want a complete chain, so you will get the chain that ends with the polytope. So if you ignore the trivial faces, then basically what I just said was a complete flag is you take a vertex, you take a one face and edge, a two face, and so on, such that each of those is always contained in the previous one. Okay, so in this picture, you have a vertex that is contained in an edge that is contained in a two face. These are what we would say what are complete flags. And then the total number of these complete flags is this flag number. So this is an interesting combinatoric quantity for the polytope, and as we have seen, it appears here in this limit theorem for the volume of the random polytope inside a polytope. Okay, and then also for this, so for the second moment and for the variance, essentially, we also have a theorem now sharp bounds. So this was a theorem due to Baroni and Leitzner much later. So this took then 7 more years to figure out essentially that we have sharp bounds also for the variance of the volume of the random polytope, and they use this to essentially derive also a central limit theorem. So maybe just to mention this, so the problem with the polytopal case is that it behaves that it does not have the same sort of localizing properties as the general curved smooth case. So if for a moment you just consider a strictly positively curved convex body, then every point on the boundary of K is an extreme point. And this essentially means that if you take a small epsilon ball around the boundary point and consider just the random points inside this ball, then basically the complete random polytope, the convex hull, is dependent locally around this point only by the points inside this epsilon ball. So in every boundary point, you have a sort of a localization property for the strictly convex, for the positively curved case. However, if you try to do the same argument with a polytope, then you notice, okay, for a polytope, the only extreme points are the vertices. And if you look at the vertices and points inside here, random points here, then actually it can happen that a new point in near another vertex suddenly has a heavy influence on the boundary structure of the random hull here, right? So in the C2 plus case, you have sort of a very strong localization property, which in the polytopal case is no longer true. And this is part of the reason why it was so much more difficult to handle this polytopal case. Okay, so this was just a heuristic observation. Okay, so these are the 2 worlds I want to compare, and in a moment move on to the spherical setup. So just to highlight this, so again, we know the rate of the volume difference, which was of the order 1 over n to the power 2 over d plus 1. And for the polytopal case, we have 1 over n times some logarithmic term. Then for the variance, we have asymptotic rates with sharp bounds, and in both cases, we had a central limit theorem. Okay. Now, I also want to mention here briefly that we have similar limit theorems for the expected number of vertices and edges and so on, so for the phase numbers. And the most complete result, I think, is due to Leitzner again. So if you have a convex body of class C2 plus, so the positively curved case, then basically the same rate you have seen in the volume case appears here, with the difference that you have to multiply by n. So you notice here we have 1 over n, and the power here is negative. So actually this is asymptotic to n to the power d minus 1 over d plus 1. So this converges to infinity. So the number of I-dimensional faces grows to infinity as n goes to infinity. And again, the affine surface area is essentially controlling the constant. And in the polytopal case, the flag number is controlling this, and we have a logarithmic rate. So also here the numbers goes to infinity, and the rate is logarithmic to the power d minus 1. So Leitzner sort of proved here the in-between cases for I between 2 and d minus 2. And the boundary cases I equals 0 and d minus 1 were already known by previous results by Baroni Viaka and Baroni Buchter. And so this sort of completed the whole picture, so that for every sort of phase number, we have this same behavior in a sense asymptotically. Okay, so just to mention this also, there is a very nice connection between the number of vertices, so for the 0 case here for I equals 0, and the volume of the random polytope. So this is the last thing I want here to highlight in the Euclidean setup. We can connect the expected volume of a random polytope with the expected number of vertices. And this is the well-known Efron identity. And the proof here is very easy and short, and I want to briefly recall it because we will use it again, or sort of, I want to talk a bit about the proof later on of another result where also these ideas play a certain role. So, okay, so we start with the expected number of vertices of our random polytope, right? And you can easily rewrite this as the expectation, where you sum up over the indicator functions of the event that the xi vector is a vertex, a corner of your random polytope. And then you rewrite this again. So the expectation is linear, so the sum you can pull outside, and then the expectation of an indicator of an event is just the probability of the event. And this event you can rewrite. So xi is a corner, is a vertex of your random polytope, if and only if all of the other points are not, if xi is not contained in the convex hull of all of the other points. So if all of the other points you can see as a sort of random polytope of n-1 points, and then if xi is not in this random polytope, then it's adding xi gives you a new corner, right? So then we can write this. So because all of the points x1 to xn are independent random points, it does not really matter. So all of these events are the same. So the sum you can just say is a multiplication by n, and then you just take the event for I equals 1. And so writing this in a more concise way, we can say this is x1 is not contained in the convex hull of all of the other points. And so this probability is just, so the probability that x1 is not in the random polytope is basically the ratio of the volume of the random polytope over the volume of the whole body. And 1 minus this ratio is the probability that a point is not inside. And then x1 is a random point, so you have to integrate, and then you get the expectation of this volume of the random polytope over the volume of K. So these are 3 lines. Every step is sort of very easy. It does not depend at all on the Euclidean structure. All we are using is basically convexity. And if you then rearrange everything, you get exactly the formula as I've written here. So in this way, you can either look at the expected volume or at the expected vertex number. And if you have one of those two, then you can derive the other one asymptotically. Okay, and this also explains where this extra 1 over n factor is coming from when you compare the rate of the vertices versus the rate of the volume difference. Okay, so this is the end of this first part. And in the next part, I just want to look at similar theorems on this in the spherical setup. So first of all, we notice that this random polytope model we have just studied in the Euclidean space is completely, makes sense, can be completely analogously be defined in the spherical space. So in the next steps, we always want to consider some fixed spherical convex body K. And we will assume that K is contained in an open half sphere as illustrated here. Now, this is not really a restriction, because you can show that if you have a spherical convex body that is positively curved in every boundary point, then it has to be contained in a half sphere. And the nice property in spherical geometry, if you have 2 points in an open half sphere, then there's always a unique geodesic connecting them. So only in the case where you consider 2 antipodal points, so say north pole and south pole of the sphere, then it can happen that you don't have a unique geodesic connecting them, right? If you have a sphere of dimension 2 greater or equal, sphere of dimension 2 or greater than 2, then antipodal points have an infinite amount of geodesics. So basically, when the distance between 2 points is pi, spherical distance, then you lose the unique geodesic property, and this can be a problem. But if you are inside an open half sphere, then you don't have this, then you have any 2 points always have a unique geodesic connecting them, and that's a very nice thing to have. Okay, so either we are looking at a convex body or at a polytope inside an open hemisphere, and then we can just define the random polytopes as a convex hull of random points, where we draw the points again uniformly with respect now to the spherical volume measure, the spherical Lebesgue measure. And then you can study the same questions. You can ask, what about the volume of these random polytopes? And the first result we obtained in this direction was in joint work with Monica Ludwig and Elisabeth Werner, where we look at exactly spherical convex bodies K of class C2+. And we show that it's essentially the same limit theorem we have seen in Euclidean space holds in spherical space. So the expectation of the volume of these random spherical polytopes behaves like this. You have the same rate of convergence, and the geometric quantity here changes. You have here the spherical Lebesgue measure, spherical volume measure, and on the right-hand side you have to replace also the volume measure with the spherical measure, and you have to replace, or what turns up here is a sort of a spherical analog of this affine surface area. Now, it's not an affine invariant anymore, so there is no affine group acting on spherical convex bodies, so you cannot expect, or it does not make sense to talk about affine invariance. However, it's still a curvature integration, where you integrate the boundary over the Gauss-Kronecker curvature to this power 1/t+1. So it's very similar to what we have seen in the Euclidean space, and we studied these quantities, which we now call floating areas, because they can also be derived from the volume of a floating body. And so in joint work with Elisabeth Werner, we have studied these not only in the spherical, but also hyperbolic spaces. And we also gave some real analytic family where we see some sort of control on the curvature. So if you have a constant curvature space, then it turns out you have a family where in curvature 0, you have the affine surface area. And if the curvature is positive, you have sort of these spherical analogs, and if the curvature is negative, you get some hyperbolic analog. So these are upper semi-continuous valuations, and if the curvature is 0, then you really also have this affine invariance property. Okay, so this was a very nice result. It tells us that the same sort of limiting behavior we have seen in Euclidean space is also true in the spherical space for these spherical random polytopes, if your underlying body is strictly positively curved. And using Efron's identity, immediately you can derive also the limit theorem for the expected number of vertices, right? So Efron's identity, you have just seen the proof. It is true also in the spherical space. We did not really use the Euclidean structure at all. And using Efron's identity, it's very clear that you sort of get the same limiting behavior again as in the Euclidean setup. Okay, then having the first moment, we in joint work with Christoph Thiele, we studied the second moment, the variance, and we also eventually were able to prove a central limit theorem. So we were only interested in the lower bound for the variance because this is enough to prove the central limit theorem, and this was sort of the goal of our paper here. So using this lower bound and some geometric estimates, which involve weighted floating bodies, I will not define them. They are some geometric tool that have been often used in connection with random polytope theory. We were able to derive a central limit theorem, which again tells us that the same sort of theorems we have seen in Euclidean space also hold true in this spherical setup. Okay. So just to mention here, all of these results on the expectations, second moment, variance bounds, and central limit theorems, in all of these, we are using a similar approach, which I just want to briefly mention here. So let's for the moment consider K is some C2 plus convex body on the sphere, and we have our random polytope. Then we can connect this spherical model with a Euclidean model of a certain kind. And so the idea is to use the so-called mnemonic projection of the sphere. So in this projection, you map one point from the sphere into the tangent plane at a fixed point via the origin, right? So every point is mapped to a fixed tangent plane. And this mnemonic projection has the nice property that if you consider a geodesic segment on the sphere, then the radial projection of this geodesic segment will be contained in a plane that goes through the origin, and then you intersect the plane with the tangent plane. So you're intersecting two planes, you will get a straight line. So this mnemonic projection has the nice property that it's a geodesic mapping. So the geodesic segments on the sphere are mapped into straight lines in Euclidean space, in the tangent plane. And this turns your spherical model again into a Euclidean model. However, you have to map your spherical Lebesgue measure, your spherical measure. So the push forward via the mnemonic projection gives you some non-uniform measure. It is still absolutely continuous with respect to the Lebesgue measure. It has a density function that is positive and well known. So in this picture, you see a color gradient here. I have deeply colored this part here, which should indicate that your measure is more concentrated here and less concentrated here. So you see more points appearing here than here, right? So there's some distortion happening here. And however, this push forward turns out to be a very well-known probabilistic distribution. It's related to the beta prime distribution with certain parameters. So essentially the takeaway is via mnemonic projection, you have your random points. If you project them, you get random points contained in some Euclidean convex body that are non-uniformly distributed with respect to some beta prime distribution. And so you can identify essentially your random, spherically random polytopes with certain restricted beta prime polytopes. And when you want to study, for instance, the spherical volume of your random polytopes, you can instead consider your non-uniform random polytopes in the Euclidean space and measure with some weighted volume, right? So the push forward of your Lebesgue measure gives you some sort of weighted volume function. And luckily, this Euclidean setup with weights was already started in part. So there is a theorem by Börwitzki, Fodor, and Hook, where essentially they show, okay, if you look at the psi weighted volume of your non-uniformly distributed random polytopes, then in expectation, you have a formula that again is very similar to what we have now seen in multiple cases. You get the same rate of convergence as we have seen before, and then you have some sort of geometric functional sort of weighted notion of affine surface area, where these weight functions phi and psi enter. Okay, and then plugging in the right weight functions, you can easily derive the spherical theorem when you have all of these identifications figured out. So so if you choose a function phi s of this form, this is essentially the Radom-Nikodym derivative of your push forward measure via the mnemonic projection of the spherical Lebesgue measure and the Euclidean Lebesgue measure. And so as it turns out, your spherical analog, your spherical analog of the affine surface area can be identified with some sort of weighted affine surface area in the Euclidean setup. And this is somehow involved. You have to understand how the spherical Gauss-Kronecker curvature changes in the mnemonic projection, and you have to express it in terms of the Euclidean Gauss-Kronecker curvature in the image. And this is what we did in this joint work, among other things, with Elisabeth. Okay, so there are some tools that we had to develop, but now these tools are there, and then it's very easy to transition from this weighted setup back onto the sphere. And we also use this approach for the variance bounds and the central limit theorem, and indeed we actually prove a much more general statement. We give a variance bounds for the weighted setup, and we give a central limit theorem for the weighted setup, which enables us not only to prove the spherical case, but other geometric cases, other non-Euclidean geometries, like hyperbolic spaces, Hilbert geometries, and stuff like this. So these are really more general statements. And yeah, this was a very nice theorem, I believe. Okay, so if we now compare again the case of the strictly positively curved case in the spherical setup with the polytopic case, basically we have an almost complete picture now in the strictly positively curved case. However, for the polytopic case, there is not much known. So I'm not even sure, I don't think the expectation is even known, but what is definitely open are variance bounds and the central limit theorem. And these are questions we have been working on at the moment. So we want to complete this picture eventually to really say, okay, also in the spherical space, we have, if you are inside an open hemisphere, then spherical polytopes behave similar to what we have seen in the Euclidean space. The spherical geometry does not destroy these observations. So there is still some work to be done in this polytopic case. And again, the polytopic case is more difficult because you have this problem with the localizing points. Okay, so in the last part of this talk, I want to now move away from the Euclidean results, right? So here we see again, the behavior is very similar to the Euclidean structure. But if you move away from the open hemisphere case and consider spherical polytopes that are not contained in an open hemisphere, then suddenly you get a different behavior in general. And the first such observation was done by Barony, Huck-Reitzner, and Schneider. They considered the whole half sphere, the whole closed half sphere. And here the remarkable observations were, first of all, if you look at a random polytope in the closed half sphere and you measure the volume, then in expectation this behaves like so. So you get the volume of the closed half space in the limit, and the rate of convergence is 1 over n. So 1 over n is faster than anything we have seen in the Euclidean results. So even for polytopes, we had 1 over n times some logarithmic factor. So this is still smaller, faster. And this is remarkable. So we have here a sort of non-Euclidean spherical convex set, the closed half sphere, which now gives us a completely different rate, something we cannot observe in Euclidean space. And using Efron's identity then tells you, okay, so the limit of the vertices actually converges to a constant. So in all of the before results, the expected number of I-dimensional faces was always converging to infinity at certain rates, but now for the half sphere case, actually all converge to constants. Okay, so this is completely different from what we have seen in any setup in the Euclidean space, and this makes this very interesting to study. And so when we saw this half sphere case, one immediately thinks, okay, there are other spherical convex sets that are not contained in an open half sphere. And the question is, what sort of behavior will they exhibit if they are not a closed half sphere? And to start this investigation, in our most recent work, we are now looking at a spherical wedge. Okay, so a spherical wedge will be something that is just an intersection of two closed half spaces. Basically, this wedge is then controlled by one angle. Here, the angle between the two hyperplanes, H1 and H2. So here you see alpha. The angle is between 0 and pi. Okay, and then our result, which we just published on arXiv, is the following. So we are looking at the expected number of facets now of our random polytope in this wedge. And it turns out that this grows logarithmic in the number of points n. So it's not constant as we have seen in the half sphere case. It's not logarithm n to the power d minus 1 as we expect to see in the polytopic case. It's strictly in between here. And we have sort of a conjecture that these wedges can give us a family of spherical convex spherical convex bodies that basically you're intersecting half spaces, closed half spaces, j of them in general position. Then we expect that the expected number of facets and expected number of I-dimensional faces behaves like logarithm n to the j minus 1. So if you have two of them, like here, then you would get 1, j minus 1 is 1. And if you have more up to d, then you would get up to the polytopic case again. And from the 0 case here, using Efron's identity, you would also see the volume case. So furthermore, we also conjecture, so we fix in this result the angle between the two hyperplanes to be orthogonal. This is just for technical reasons because our calculations were already involved enough. But essentially, we believe that this angle should not play a role in the constants here appearing, or even in this more general case. So the angles between the actual angles between the half spaces should not enter in these limit theorems, we believe. And the reason is basically in the polytopal setup, we see something similar happening. So we see that the constants are dependent on the combinatoric structure, but not on the actual positioning of the vertices. So as long as you wiggle your vertices of your polytope around a bit such that the convex, the combinatoric structure is not changed, the constants don't change either in these approximation theorems. So this is the reason why we believe that these arrow terms here should not depend on the actual angles here. Okay, so this is the first step into this. Well, we hope we can eventually prove all of these statements, and this should give us some nice transitioning, or give us a family that transitions between this exceptional half sphere case and the polytopal case. Okay, so in the last 10-15 minutes, let me go over the ideas behind this proof of this statement. And to start off, we want to look at this identity in a way that mimics in a way this Efron proof, Efron identity proof. So we want to look at the expectation of the number of facets of our random wedge. And we write this as the sum of the indicators of the event that d vertices are a facet of our random polytope. Okay, so we order indices I1 up to ID, and of course, because our random points x, I are independent, this again can be reduced to the case where you look at the event that the first d vertices build a facet and integrate over these vertices. So you integrate over x1 or xd with respect to the spherical measure, and you have n choose d cases. Okay, so with probability 1, these d vertices x1 to xd are in an hyperplane. They span a hyperplane because they are a facet with probability 1, so the facet is contained in a hyperplane. And then the condition that these points are a facet is essentially saying that all the other points are on one side of this hyperplane. So all of these points xd plus 1 to xn are either in h plus or h minus, which indicate the two closed half spheres bounded by this hyperplane. And then you can use a Blaschke-Bedkamp formula, which is you want instead to integrate over all of the points in this wedge. You want to first integrate over all of the half spaces h, and then integrate over the half spaces intersected with the wedge, the points x1 to xd. So this is an integral geometric formula that is well known in Euclidean space, and there is a spherical analog also. When you use this, there is some Jacobian factor entering here, which is this nabla d of x1 to xd, which is essentially related to the volume of the parallelotope spanned by x1 and xd. You can think of it as a sort of determinant of the matrix of x1 to xd. So this is some Jacobian factor. you integrate this over this wedges intersected with the hyperplane, and then the probability is now just the probability of one of those points being either in H plus or H minus, and since they're all independent, you then take n minus d times this. So this is either the points are in H plus, then you have the ratio between the wedge intersected with this half space, or the opposite case. Okay, so this is the first formula we have to derive here. And to just write this in a more simple way, we now call this first integral here I1, and the volume of this wedge intersected with another half space will be called I2. Okay, so we have to find estimates for I1 and I2 to eventually find the limiting behavior of this integration here. Okay, so to understand these functionals I1 and I2, they are dependent on the direction u of the normal vector u of your hyperplane. The first step is to understand the geometry of this wedge intersected with a hyperplane or a closed half space. And actually, these sets are quite simple. So if you look at this wedge and you intersect it with a hyperplane, then basically you have the wedge, which is the intersection of two half spheres. And then you intersect with another half sphere. So essentially you are intersecting three hyperplanes. And if you're looking at the normals of these hyperplanes, they span a spherical triangle. And so this, this sort of intersection here is the polar of a spherical triangle. So really this is controlled by the angles of a spherical triangle. And you have three angles here in general. You know the alpha. This is the angle between H1 and H2. And then you have another hyperplane HU, which is essentially controlled by the angle phi and psi as written in this sketch. So phi measures sort of the angle or the distance, spherical distance from this vertex to HU along H1, and psi measures the angle between H1 and HU. So, and if you intersect your wedge with the hyperplane, then you obtain another wedge, a d-1 dimensional wedge, where the angle, the beta, where the opening angle is controlled by beta. And since this is one side of your spherical triangle, this can be expressed by the three other angles, alpha, psi, and phi. And since alpha is pi over 2, this is just a simple spherical trigonometry to figure out that the tangent of beta is tangent of phi over cosine of psi. So your normal vector u of your hyperplane gives rise to angles phi and psi, and they can be translated into expressing this this length of this spherical wedge. Okay, and using this information, then you can start bounding your integral terms. So I1 was this integral over the Jacobian factor coming from the spherical Blaschke-Bekantian formula. And we find one absolute upper bound in this term. It's dependent on beta, so the angle of your intersection, to the power d+1, and you have some dimensional constant appearing here, AD, which we can write down, but not we cannot explicitly calculate it. So this is the downside of our theory. We were not able, unless in the two-dimensional case, to evaluate the exact value of these constants, these dimensional constants. Yeah, if anybody has an idea, so they are quite complicated, even in dimension 3 already. You have some sort of volume of a parallelotope that is generated by these random points, random vertices u1, c1, and 1. So you're in a hyperplane at distance 1 from the origin. And the U ones are uniformly distributed, and the C ones are d minus 2-dimensional random vectors that are beta prime distributed with a certain parameter. So this was escaped for now our grasp, but hopefully at some point we will be able to give explicit values to this. Yeah, so there are some integrals that we cannot evaluate at the moment. However, if phi and psi are small, then also the angle beta of our wedge is small, and then we have more precise information. So then this upper bound is essentially sharp, and this is basically controlled by phi to the power d plus 1 asymptotically. Okay, so this is one of the key lemmas here. And the second key lemma is for the second quantity I2 here. So remember that I2 was just the spherical volume of our spherical wedge intersected with another half, with a random half space, random half sphere. And as I mentioned, this is essentially the polar of a spherical triangle. And so the area of a spherical triangle is well known. There is a nice formula depending on the angles of this. And this is basically what you get. You get the angle psi minus the arccosine of cosine phi and sine psi in this way. And in higher dimensions, you just have to renormalize the volume of the whole sphere over the volume of a two-sphere. Then we were able to figure out analytically a lower bound, an absolute lower bound for all of the phi and psi. And if phi and psi are small enough, then asymptotically they behave like phi squared over psi times psi. Okay, so these are the two lemmas that you have to prove, which are quite involved and technical. But once you have this, then you can proceed with estimating your expected number of facets. Okay, so we want to rewrite this. First of all, as I mentioned, so these two quantities, they depend only on these angles phi and psi. So we are using, instead of the whole sphere, we are using polar coordinates to integrate over a d minus 2-dimensional sphere, and then phi and psi in the other two coordinates. And if you're using spherical coordinates, you get the Jacobian of term sine psi to the d minus 2 and sine phi to the power d minus 2 here. And then I1 and I2 are the same as before. And then using symmetry of your spherical wedge. So this spherical wedge you can reflect in various ways. So using the symmetries of this set, you can further reduce this to an integral over I1 times this. Okay, so I hide here all of the constants depending on the dimension. In the paper, we have this precise, and we obtain the precise constants, but for now, we just want to look at the asymptotics of this quantity. Okay, so here we are at this, and now we can use our lemma to use the estimates on I1 and I2. So I just copied the last line over. So we want to bound I1 and I2, and let's say we bound it from below. If we want to bound from below, then we can restrict the integration domain here to something that is bounded by epsilon, so very close to epsilon. And then we can replace I1 by something that is asymptotic to phi over d plus 1. And our sine phi here is essentially a phi over d minus 2. So we get a phi to the power d 2d minus 1. And here we had our phi squared over psi asymptotically. So up to some eta constant here, we get this quantity. And then just using the normal transformation formula for integrals, if you replace eta phi squared by s over n, you arrive at this expression. You get an additional 1 over n to the d factor here by this substitution, and then n over 1 over n over d times the binomial converges as n goes to infinity. And this integral term here is maybe not so trivial, but there are some tools to do here. So basically you are integrating here as n goes to infinity from 0 to infinity, this integral here. And it turns out this goes to infinity at the rate of logarithm n. So this is how we eventually get a lower bound of order logarithm n. And for the upper bound, you do pretty much the same. So you also want to concentrate on the integral here from 0 to epsilon for epsilon small. And then you have to also consider the other parts, right? So on the other parts, you can either bound phi or psi away from 0. And if you eventually look at this again, and for instance, if t is bounded away from 0, then you can estimate this. So if t is a constant here, then this integration can just vanishes. And then you have an integral from 0 to infinity over s to the power d minus 1, 1 minus constant times s over n to the power n. This is the gamma function, right? So this is the gamma function is convergent. So this is why we will get some constant term. So only in the case where phi and psi are small, we get this logarithmic convergence behavior. And for all of the other integration parts, we can bound it by some constant. And so this is dominated by this part here. Okay, so this is how the proof works. I skipped all of the technical details. It was already quite involved. This whole theory started a long time ago, 2 years ago, in an Oberwolfach meeting. And we have many co-authors here. So this is basically the group that sat down at that point and started thinking about this. And it took us a long time to really fix all of the technical details in the end. But now it's finished, and we hope to move on into other cases. So here you see again this random polytope in this wedge, and here you see the normalic projection. And I just want to give you this two-dimensional picture because there is another nice observation here. So if you just look at the planar case, in the two-dimensional case, then the expected number of vertices is of course the same as the expected number of edges. And we know the constant explicit in the two-dimensional case, which is 4/3 in the end. So the rate here is controlled by 4/3 logarithm n. And you can compare this with the Euclidean results. And there we know that the rate is controlled by 2 times the number of vertices of your original polygon over 3. And since the polygon with the lowest number of vertices is the triangle in the plane, you will always have at least 6/3 here. So in a sense, your spherical wedge is extending this family by sort of a polygon, if you want, with only 2 vertices, and it's fitting very nicely in this, from this point of view, into this theory. So you have a sort of the sphere allows us a certain of non-Euclidean polygon, which only has 2 vertices, which breaks this lower bound that we see in Euclidean space for the triangle. Okay, so this was just another observation we had. Coming to the end of this presentation, let me just mention that in this theory of spherical convex polytopes, we also look at these random polytopes where your points are not drawn from the inside, but on the boundary of K. We have some recent results here for central limit theorems in the strictly positively curved case with Daniel Rosen and Thiele. So I did not mention this polytopal model, but this is also very interesting in the strictly curved case, where you basically just choose points from the boundary. And these theorems and most of the earlier results I've shown you, we not only know in the spherical space, we also know them in other geometries like Hilbert geometries, hyperbolic spaces. So in this picture, you see the hyperboloid model, and this just illustrates this hyperbolic case. Now, for the polytopal cases, even in the hyperbolic space, we don't have much information. And this is probably what I would hope to see in the next years to come, more results in this non-Euclidean setup for the polytopes. So this is sort of a gap that we have in the theory, I believe, where we are working at the moment. And this is something that hopefully can be solved soon. And another step forward is, of course, studying these non-Euclidean sets that behave differently from everything we have seen in the Euclidean setup. So we have seen now a family of wedges, which in this one particular case already gives us some new information. And there are, of course, other quantities we want to study on these wedges and on more general wedges. And this is sort of where we also hope to proceed in the future. Okay, so this is the end of this talk, and thank you very much for paying attention.
All right, Florian, thank you very much for this presentation. So now if somebody has a question, you can open your microphone and ask. No? Okay, then if nobody has a question, I do have some question.
Yes.
You were doing everything in the sphere of radius 1, right? So the spherical model, you consider the sphere of radius 1. So is there some way like to consider a sphere of radius r in such a way that you normalize so that when the radius goes to infinity, everything becomes flatter and you go back to the Euclidean model? So you will have something that goes from the spherical model to the Euclidean model?
So it should be possible. So we do this when we look at the affine surface area or the analogs of this affine surface area. I guess you have to, so you have a convex body and you want to consider or you have to specify in this limiting behavior how you look at your convex body in the different radii, right? So one way would be to look at the convex cone in the projective case and intersect it with the sphere or the hyperplane, sphere of different radius or the hyperplane. And this would give you a natural way to identify the convex body for different curvature cases. And then our theorem, well, we have stated it for the case where the curvature is 1. I guess one should be able to maybe figure out how it changes with the curvature. So I would say maybe one has to be careful at some point, but it should be possible. So basically, I think, for instance, if you look at the volume difference, then you probably can write down something similar to this limiting formula we have seen. So a real analytic version of our limiting formula. So something like the expectation of our d-dimensional volume in a lambda curved space of our random polytope should be something like the volume, the lambda volume of K minus the affine surface area lambda version of this affine surface area of K, some dimensional constant here, the volume, d-dimensional lambda volume of K over N to the 2 over d plus 1 times some lower order terms. So this would be a real analytic version of this limiting formula, and this is easy to derive from the tools we have now, because we have a lambda so we do know the lambda volume. This is the intrinsic volume of sort of the space form, d-dimensional space form of constant curvature lambda, and we have these lambda family of floating areas. And you can identify all of this with certain Euclidean models. So you can find some Euclidean models of your space forms, and then basically this formula should follow from essentially the same way we proved the spherical case.
Okay, so when you said that in the closed half sphere you had a behavior that you didn't see before in the Euclidean model. Maybe in this way you could find what's the Euclidean model that will correspond to that closed half sphere and will have a similar behavior. Or
yes, so I mean, okay, so you can define a Euclidean model, which is basically the spherical space as a Euclidean model. For the half sphere, you would just get the whole space, right? And for the wedge, you would get something like this infinite set here. So something that is bounded and is infinite, and you have some finite probability measure here. But as soon as you are in a compact polytope case, you are in the Euclidean setup. So I see your point that you can think of this as in a Euclidean way, and I guess once if you look at the spherical setup and you look at the spherical convex bodies that are not contained in an open half sphere, in the Euclidean setup you would via a mnemonic projection get something that is unbounded in general. And basically, I guess you could then look at random polytope theory in unbounded convex sets with some weight functions that give you a finite probability measure.
Yeah.
Yeah. So I guess the advantage of looking at the sphere first is that you have the geometry of the sphere to work with. If you do it for weighted functions, arbitrary weight functions, then it might happen that you have less information a priori. So I don't know. It's probably possible to look at this in a more general setup in the Euclidean space with weights. Yes.
All right. And I had another question. In all your models, the dimension is fixed, and you move just the number of points. You make them grow to infinity.
Yes.
Are there results where you link both? So maybe you have a sequence of convex bodies, of underlying convex bodies, and in each dimension, you take a number of points which is related to the dimension and find some limited result there, or
I know there are results in the Euclidean setup, and I'm not aware of results of this form in the non-Euclidean setup yet. It's definitely something to investigate, I think. But I'm not sure if anybody has looked into this yet. So there are a lot of natural questions that we have seen in the Euclidean space that can be translated into the non-Euclidean geometries as well, and where we have nobody apparently has thought of this yet, but I think this is a very good question to investigate. Yes.
Okay. Thanks. So I don't have any other questions. If anybody has a question, please ask. No, then thank you for this nice talk again, Florian.
Thank you.